There are three different types of distributions that we need to distinguish. The first distribution is for the population. It's the probability distribution that we sample from. For certain cases, we know that the population has a normal distribution with a mean of mu and a standard deviation of sigma. But in other cases, we don't know that the population is normal. Maybe it's skewed or bimodal or uniform or some shape we haven't even studied. But even for those populations, you could find a mean and a standard deviation, even if you can't describe their shape. When you think population distribution, think that big bucket with everyone that we could sample from. When you go in and take a sample, collect some experimental units, that gives you the data distribution. It's what you see in the sample. The data distribution, you can describe the mean, which is called X bar, and the standard deviation, which is called S. Then finally, there's this thing called the sampling distribution. And here we'll talk about the sampling distribution of the sample mean. Remember, a statistic, one type, would be a mean. So we're thinking the sampling distribution is the distribution of the sample mean, X bar. Central limit theorem says that X bar has a normal distribution with mean mu and standard error sigma over the square root of n. There's a lot of vocabulary going on right here. Sigma over the root n is what we call a standard error. Sigma itself is what we call the standard deviation. It's very important that you remember the difference between standard error and standard deviation. For the error, divide by the square root of the sample size. For this to hold, there's two requirements. The first requirement is simple random sampling. And the second requirement falls into an OR case. You can say either the original population is normal. That would be this case. The original population was known to be normal. Or, if that doesn't hold, the other requirement would be that you have a sample size equal to 30 or larger. That means that you sampled 30 or more subjects. According to a 1999 report by the Institute of Medicine, as many as 98,000 Americans were dying every year because of medical mistakes. But a reasonable estimate is that medical mistakes now kill around 200,000 Americans every year. That would make them one of the leading causes of death in the United States. Why have these mistakes been so hard to prevent? So what do we do to be safer? Many smart people have tackled this question. One person at Johns Hopkins developed a checklist shown to bring hospital-acquired infections down to close to zero. There are rules against disturbing nurses while they dispense medications, and software that warns doctors when patients' prescriptions will interact badly. There are policies designed to empower nurses to confront doctors if they see something wrong, even if a senior doctor is at fault. An analysis of the number of patient deaths due to medical error per year over the past decade finds a population mean of 190,000 and a standard deviation of 101.1. Death due to medical error is skewed right. A researcher randomly sampled 30 months out of the past decade and have found an average of 888,000 patients died due to medical error, with a standard deviation of 120.5. Let's go through and try to identify our three types of distributions. We should first discuss what our random variable x is representing. We were looking at the number of patient deaths due to medical error. To describe the shape, center, and spread of the population distribution, we need to come back into the problem setting. It says that death due to the medical error is skewed right, so the shape here would be skewed right. Let's come back and look at population distribution. We said that there's two ways to describe the population distribution. You can say that it's normal mu sigma, but if you don't know it's normal, for example, if it were skewed right, you only report mu and sigma. So that's why over here when it says describe the shape, skewed right, we'll just say the center is mu equal a specific number and the spread is sigma equal a specific number. The problem told us that the mean was 197,000 and the standard deviation was 101.1. Describe the center and spread of the sample distribution. For this, we should also report a mean and a standard deviation, but since it's for a sample, we use X bar and S. It says that 30 months were sampled, and the average was 8,888, with a standard deviation of 120.5. Lastly, we should describe the shape, center, and spread of the sampling distribution of the sample statistic, and in this case, the statistic is a mean. For this, we'll use central limit theorem, which says that X bar is normally distributed with mean mu and standard error sigma over the square root of n. If you're looking for the number to plug in here, you have to decide whether to use this mean or this mean. And the mean you should use is the one that says mu, the one for the population. Same thing with the sigma. You do not want to use the S, you want to use the sigma when you plug these in. The other thing that we need besides mu and sigma is n, the sample size, and the problem said 30 months, so we'll be plugging a 30 in here. For this to be true, we have to check several assumptions. The first assumption would be that there's a random sample. And if we come in here in the problem, it says that they randomly sampled 30 months, so we've met this. The second is that the original population is normal, but over here it's not normal, it's skewed right, so we don't meet that. But it's an or statement. It says normal or you sampled 30 or more months, and we know 30 months were sampled, so the n greater than or equal to 30 assumption was met. Therefore, this statement is true. One of the last things I'll point out is the difference in vocabulary. The standard deviation is this. The standard error equals the standard deviation divided by the square root of n. So this is your standard error, and it says that up here. Standard error, that's the 101 divided by square root 30. Standard deviation is just the 101.1 that you're seeing right here. Here's the second example. 3 of the 30 subspecies of white-tailed deer are found here in Florida. The coastal white-tailed deer found in the Panhandle, the key deer with a limited distribution on Big Pine Key, and the Florida white-tailed deer found throughout the peninsula. White-tailed deer males have antlers which they shed each winter. 1 in 10,000 females may also grow antlers. In the 1930s, during a statewide effort to eradicate tick-borne diseases, Florida's deer population was almost wiped out. Down to a count of 20,000, the state purchased white-tailed deer from a farm in Wisconsin and introduced them into unoccupied areas in Florida. Efforts were successful, and today population estimates exceed 700,000 deer statewide. The mean number of deer in Florida's 67 counties is normally distributed with the mean and standard deviation given. This is based on census information for the population. We know the random variable x is the number of deer in one of the counties in Florida, so we'll say x equals number of deer in a Florida county. We also can talk about the population distribution. It says up here that we know it's normally distributed, so the number of deer has a normal distribution with a mean of 10,450 and a standard deviation of 100. Remember, the first one is your mu and the second one is your sigma when you're talking about population distribution. Coming back to our page with the 3 different types of distribution, we're now in this case. We know the original population was normally distributed. So when we're looking at the sampling distribution, we know that we're going to be meeting this assumption. These two go together, and these two go together. Let's come back into the problem and keep reading. Suppose the researchers instead had estimated this mean using a random sample of 40 counties. Suppose the sample had a sample mean, which would be X bar of 10,000, and a standard deviation of 150. These numbers came from a sample that makes them part of the data distribution. Now we can describe the center and spread of the sampling distribution of the sample statistic. And in this case, the statistic is a mean. To describe this, we'll use central limit theorem, which says that the mean, x bar, has a normal distribution centered at mu and standard error sigma over the square root of n. Remember, mu is right here and sigma is right here. We'll plug these numbers in, along with the n value of 40 counties. For this to hold, we need to check our assumptions. The first assumption is that we have simple random sampling, and it says random sample of 40 counties. The second assumption is that you need an originally normal distribution, and if you come into the problem setting, it says that for the population for all 67 counties, there's a normal distribution. Notice that if you meet this particular assumption, you could have had a sample of any size. Yes, 40 is bigger than 30, but you could have even had smaller than 30 sample sizes if you meet the originally normal population. You could sample 20 counties or even 10 counties and still be okay to make this particular statement. Let's start working out probabilities for these problems. If the problem refers to a single subject, use the Xbar-Z-Table steps that I've already taught you. Notice it says a subject, only one. What is the probability that A, just one, randomly selected Florida county has less than 10,200 deer? That's the probability that X is less than 10,200. We know that our steps say to write this in terms of X, which we've done. Then it says convert to a Z. This is the probability that Z is less than the observation, 10,200, minus a mean divided by a standard deviation. Keep in mind that it said just one county, a single subject. Let's go grab our mean and standard deviation. The problem we were looking at said one particular Florida county. So when you're trying to decide whether to use this or this distribution, you're going to have to think about the wording. If you're looking at one at a time, that's only one X. If you're looking at groups, that's a group or an X bar. Since we're looking at one, we're going to use this particular mean and standard deviation. So we're going to subtract the mean, 10,450, and divide by the standard deviation, 100. This gives back a z-score of negative 2.50. Going to the z-table, we see negative 2.50 occurs with probability 0.0062. So there's about a 6.2% chance that just one county at a time would have less than 10,000 deer. The second type of problem will refer to a group, and for these you're going to use, and this didn't copy right, you're going to use Xbar-Z-Table steps. And the keywords that you'll be looking for here are groups or average. So looking at this one, what is the probability that the average deer population for not one county but 40 counties is less than 10,200? This is a group. So we're looking for the probability that the average X bar for this group of 40 is less than 10,200. Be careful on your notation there. We're now doing Xbar-Z-Table steps. Well, we've written it in terms of X bar. Our next step is to go to the Z. To convert to a Z, you take your observation and you subtract a mean and divide by a standard deviation, which we're now calling a standard error. Let's go and find what these two values are. Coming back to this page, if you're talking about one county, a county, you use X. When you're talking about the average of a group of randomly selected counties, such as 40 random counties, you're talking about an X bar. So we're going to be using this distribution to work out the probability. So we have our observation. We're going to subtract the mean of 10,450 and divide by the standard error, 100 divided by the square root of 40. When you type this in the calculator, you're going to need to type in 10,200 minus 10,450 divided by parentheses 100 divided by square root of 40. Close parentheses. Parentheses on the numerator, divide, parentheses on the denominator. This gives back a z-score of negative 15.81. If you think about the z-distribution, it's centered at 0 with standard deviation 1, so we can run up to 3 on the upper end and -3 on the lower end. The probability of being -3 or smaller is very tiny. We even said it was an outlier. So if we're looking for a -15.81 way out here, can you see that this area, that this probability is practically 0? Just to show you on the z-table, the largest z-score that you're going to see is -3.49, and the probability of being at this z-score smaller is 0.0002. So if you jump all the way out to our z-score of -15.81, it's going to happen with probability almost equal to 0. This would be our final answer. Here's another example. What is the probability that the average deer population for 40 counties is between these two numbers? Because you're seeing average, you should be thinking Xbar-Z-Table steps. To write this with the correct notation, we're looking for the probability of being between 10,000 and 12,000. On the X-bar curve, we're looking for this shaded region. To look this up in the z-table, though, what you're going to have to do is find the probability of being at 12,000 and smaller, and then subtract out the probability of being at 10,000 and smaller. Subtract this part off. When you subtract this out, it leaves over the central portion that you wanted to find. So we've now completed the X-bar step. We're now ready to convert to the z-distribution. To do this, we're going to have to subtract and divide. To decide which distribution to use, we need to remember that we're looking at a group, a sample of 40 counties. That tells us again we should be using the X-bar distribution from Part D. So we're going to subtract 10,450 and divide by the standard error of 100 over the square root of 40. That takes care of this X-bar. Now we need to do the second X-bar. So we take the observation of 10,000, subtract the mean of 10,450, and divide by the standard error of 100 over the square root of 40. The first one gives a z-score of 1.58, and the second one gives a z-score of -1.90. So we've completed the X-bar step, we've converted to the z, we're now ready to go to the table. 1.58 gives a probability of 0.9429. Now we're going to look up the -1.90. -1.90 gives a probability of 0.0287. Subtracting these two numbers, we see that the final answer is 0.9142. There is about a 92% chance that the average deer population for 40 randomly selected counties is between 10,000 and 12,000. Here's the second example. Need a small but powerful carry gun? Look no further. The Kimber Solo CDP has a single action striker-fired trigger with a smooth 7-pound pull. Kimber employed their extreme knowledge of aluminum alloy frame design to create a pistol weighing a mere 17 ounces, while still having a stainless steel slide and 2.7-inch barrel. Not wanting to leave the 10%ers behind, Kimber made both the thumb safety lever and magazine release button ambidextrous. The gun's overall features are small but not tiny, with a length of 5.5 inches and a height just under 4 inches. One of the major complaints of many small pistols is the lack of good sights. The Solo sights are excellent. They are dovetailed into the slide, low profile, and have a white outline with tritium inserts, allowing them to easily be seen in low light conditions. The Kimber custom shop produces the Solo CDP. We have read the gun weighs 17 ounces, but there will be variability in the weight. It is a random variable. That right there tells us what our variable x is. We know that the random variable x is the weight of the Kimber Solo CDP. The distribution of weight for these handguns is approximately normal with a mean 18 ounces and standard deviation 1.5 ounces. That is the center and spread of the population distribution along with the shape of normality. So we know that X has a normal distribution with mu equal 18 and sigma equal 1.5. One of the things to remember too is that X means 1. This is for a handgun. Suppose we randomly sample 5 solo CDPs. Describe the center and spread, standard error, of the sampling distribution of the sample mean. Well, the sample mean is X bar, and by central limit theorem, it's normal with a center at mu and standard error sigma over the square root of n. We know mu, we know sigma, and we know that they had 5 of these solo CDPs. That's our sample size n. Let's plug this in. For us to be allowed to make this statement, we have to meet 2 conditions. The first is simple random sampling, and it says randomly sampled. The second is an originally normal distribution. And if we come up here in the problem setting and read, it says the weight of distributions for these handguns is approximately normal, so we know it's normally distributed. Remember, the other thing you could have gotten away with if it was not normal is that n is greater than or equal to 30. Here we don't need that because it's originally normal. We're allowed to have an n of 5, less than 30, because the originally normal was met. One last thing we should point out before we move on is that X bar is no longer dealing with 1. It's dealing with a group, and here we're dealing with groups of 5. So we're going to be looking for words like average or group when we work out word problems for using this distribution, and we're going to be looking for words like A when we work out word problems with this distribution. Find the probability that that A, randomly selected solo CDP, weighs more than 17 ounces. Because we're dealing with 1, we're going to use the X-Z-Table steps. The other thing that we know is that we'll be using the X is normal 18 1.5. Using our steps, we want to write this in terms of X, so we're looking for the probability that X is greater than 17. You could even say greater than or equal to 17. Remember, if you go to look this up in the X distribution and being at 17 or larger, you're not going to be able to find it. What you're actually going to have to look up is 100% minus this value, which would leave over the value in black. So we need to convert this to say 1 minus the probability of being less than or equal to 17. That's X. We're now ready to convert to a Z. This is 1 minus the probability that Z is less than or equal to the observation minus the mean of 18 divided by the standard deviation of 1.5. This simplifies to the probability that Z is less than or equal to negative 0.67. We've converted to the Z. We're now ready to go to the table. Negative 0.67. Remember, the ones and tens position is here, the hundredth position is here. So negative 0.67 has a probability of 0.2514. This gives a final answer of 0.7486. So there's about a 75% chance that the gun could weigh more than 17 ounces. Find the probability that an average of 5 randomly selected solo CDPs weigh more than 17 ounces. Notice it's saying the word average. It's talking about not 1, but 5 of the solo CDPs. This means we're using a group. When there's a group, we said that we were going to be talking about the X-bar distribution. This means we're going to be using the Xbar-Z-Table steps. Starting out, we want the probability that X bar is greater than or equal to 17. Again, you're going to have to rewrite this as 1 minus the probability of being less than it so that you can find that value in the table. Now that we've written in terms of X bar, we can convert to a Z. This is 1 minus the probability that z is less than or equal to the observation of 17 minus the mean of 18 divided by the standard error of 1.5 over the square root of 5. That z-score simplifies to the number negative 1.49. And now that we've written it in terms of x converted to a z, we're ready to go to the table. Negative 1.49 occurs with probability 0.0681. This gives a final answer of 0.9319. So for a group of 5, there's a 93% chance that their average would be more than 17 ounces. These are the works cited used in this lecture.